give you the basic of a TCP control. Okay, TCP control has very important features called timeout. Okay, later I will keep mentioning this called something called TCP timeout or something like that. Okay, so that timeout mechanism in the last lecture we have already covered why and how. Okay, we need it, and how means that also plus where. Okay, where the timer should be implemented after the timer is go off. Okay, so when you should retransmit or what you should do. Okay, we can summarize it in this diagram. Okay, so what is this diagram? This diagram is a case that we don't have any corruption now. We only have a packet loss. Okay, so what is the meaning of a packet loss? I artificially inject a loss there. Okay, suppose that the first round of message is successfully delivered. No problem. I have a sending of the message. I have a reply. Okay, then what happened if I lost the reply? Yeah, here. I lost the reply on this side because this side don't know whether I lost the reply or I lost the data. What I can perceive is I don't have any replies. Okay, so then I will retransmit the same guy again. So I want to echo one more time that in the TCP layer or the transport layer, why we need more memory than unreliable version? Because the reliable version always need to retransmit things. Okay, so whenever I will retransmit, I need to keep a copy of the data that I want to send out. Okay, so with this copy, I retransmit the copy, and everything goes normal. Okay, so any questions? Should be okay, huh? No question, huh? Okay. What's next? Next is horrible. So what's the horrible stuff? The horrible stuff is, I don't know why. Okay. This time is acknowledgement loss. Okay. So loss very horrible, right? It's just a normal evolution of a story. Now the stories in evolutions like this is I still cannot get any replies, but the reality is the replies lost, or the ACK is lost. Now I still try to reply with the same data, with the same thing that I just sent. Now what happened to the receiver? The receiver not going to deliver this guy to the application layer anymore. Okay, compared to the previous case. Previous case is the sender asks for sequence number 1. I cannot get it. Okay, so this receiver know nothing. Okay, I'm still waiting for acknowledgement number 1. So whenever the data with acknowledgement, no, sorry, it's sequence number. Okay, acknowledgement is here, right? Sequence number is number 1. Then you should treat this as the first copy that I received, and I deliver this data to the application layer. And the slight change here is the receiver don't know what's going on previously, but what it perceives is, I mean the receiver. The receiver perceives is, I don't know what happened, but it seems that my previous ACK is corrupted or lost, right? So then I receive a repeated sequence number. Okay, with this repeated sequence number, don't do anything. Just do the retransmission of the ACK. What is the meaning of don't do anything? Don't deliver this data to the application layer. If you deliver the application layer, then you have duplicated copies. Okay, so here I already delivered once. I don't deliver twice. Okay. Any questions? Any questions? Okay, so if you don't have any questions, then I change the game. So what is the meaning of changing the game? I have different speed. Okay, so can you see a difference? So what is the difference here? This is previous, this is next. Okay, I change the speed of one guy. Okay, the receiver side is getting slower than before. Okay, can you see again? Previous, next. Okay, so you can see now it is slower, taking longer time. Okay, now this is the problem of our original idea of having timeout, right? Having timeout, what is the longest time that I have to wait for? No one can tell you, right? No one can tell you when we should fire alarm and alarm saying, oh, we transmit. Okay, so we can only have some reasonable estimate. Okay, in the TCP, TCP is doing a fantastic job. Okay, he is doing interpolation or some other numerical analysis over the receiver side acknowledgement timestamp. Okay, but here we don't have such a complex analysis, so we always fix it to a constant. Let's say the constant is this red arrow. Okay, this is a constant. Now the constant is already not enough for the slower receiver. Okay, so the receiver says something which is slower than before, and the problem is when a timer is fire, okay, it's go off. What happens is eventually you will later receive the ACK, or I should say, when you fire the retransmission, the acknowledgement is still going on the way. It's still on the way. The ACK is still on the way, but the timer is already go off. So what should you do? Okay, I don't know the reality. Okay, as if I cover here, you don't know what is going on. So then the sender will consider that the ACK or the data itself is lost. So I have to retransmit the data, sequence number 1. Okay? And we are being very lucky. Okay? After I send out the data, immediately I receive the ACK. Okay? So you as a receiver, okay, don't know about it, but the sender know about it now. Oh, ACK has come. But sorry, this is a previous case. Previous ACK. Okay? So what's going on here? For the sender, we will treat everything as okay, right? I send out sequence 0, receive reply of 0. Send out 1, I lost the reply, I don't know why. Then I send out 1 again, immediately I receive ACK. Good. For me, the case is closed. Okay, so let's imagine that we don't have further data to send. Okay, this is an assumption. We can break this assumption later. Okay, so we have this assumption that I don't have anything to send now. Stop. Okay, so how about the receiver? The receiver case is not that simple. Okay, the receiver is going on with the receive of the first data 0. I send on ACK. I don't need to care about this because I don't implement any timer. Then I receive sequence number 1 of the data. Okay, I send out the replies. And later on, I receive sequence number 1 data again. Okay, so I am the receiver. What should I think of? I think of as oh, maybe the previous case. Okay, I send out the ACK. The other side cannot receive it. Okay, then what should I do? I will transmit the ACK. Okay, so this is what I think. But the reality is not that simple. The reality is because I'm sending something slow, which is slower than expected, later on I have the next data coming in. Okay? So this is the false alarm. Okay? The next data sequence number 1 is false alarm, so I still reply that, no problem. But how about the sender? Now sender is in a very embarrassing moment. Okay? The embarrassing moment is like this. I already don't have anything to send. Okay, why? Because I know that the previous 0 is being acknowledged. The previous 1, although it's lost once, immediately I receive the reply. So the 2 messages I want to send out are already completed. Why I still have another ACK? Okay, and the reason is here. Okay, this is the only reason. Okay, but as a designer of the sender side, okay, we don't need to care about the reality, right? The reality is that because of speed change, okay. Now I disregard this fact, okay. I take a look at this simple, with the simple idea that I send out something, I receive replies, case code, okay. Because you send me the reply, right? You send me the reply. That means that you will also have received it, okay. If I receive further ACK, I shouldn't respond to you anymore. Understand? And this is a very important point, okay? Why I keep ignoring the last guy? Because I already received ACK of sequence number 1. ACK of sequence number 1 meaning that you receive it. Okay? You receive it. This is your receipt. Okay, I receive once. If I receive the same receive twice, okay, that means there's something wrong in the middle. And this is the illustration. Okay, then the sender should ignore it completely. Okay, any questions? No. No. Any questions?
If between the period that you receive two ACK with sequence 1, you receive sequence 0 with number 0 again in this period. So we will regard the latter one.
Yes, very good question. But can you illustrate why? Why the reality gives me a 0 in between it?
Maybe there are different data link, and one data link is quick.
No. If there's let's say the router drop a packet for you, the router won't repeat it for you. So the one which controls the retransmission is only the endpoints. Okay. So you're very close to some really tricky point here. Okay. A tricky point here. I never asked this question in examination, but I want you to memorize it. Okay. This figure has a serious bug. And this protocol has a serious bug. The bug is, can I have two data traveling at different speed? So that they won't go parallel anymore. They will go in a way that have cross. Then the whole protocol breaks. The whole protocol breaks down. Okay? And the why will break down, okay, he already mentioned it. Okay? You will have a case that I receive your ACK1 and suddenly I receive ACK0. And then it's totally makes not many sense, right? I receive ACK of 1 here and suddenly I receive 0 in between it. And he asks, will it happen? And he don't give me an example. I give you an example. Okay? It's somehow the message, okay, go not in an order, not FIFO. Okay? So here, this protocol has a very strong assumption that it should go in FIFO. Okay? You cannot have a sending 2 messages at a time and then they go out of order. Okay? You can draw some figure by yourself. What if it go out of order? Then totally breakdowns of this protocol. This protocol sucks. Okay? Wow. Every time I take 10 minutes to talk about it. Okay, this diagram I copied it from a textbook. Okay, so don't worry. Only half of the stage is only important, right? Because it's just a mirror, right? Here is mirror. Here is mirror. Okay, so very very easy to understand that because we can only consider some extreme case. Okay, some normal cases like I receive something good, I wait for some data and send out a data sequence 0, then I wait for ACK 0. This is normal path. Okay, some of the path you already seen before. Okay, let's say from ACK 0 migrate to application, sending a new piece of data. So I generate data 1 and continue the journey. And what's new is, what is the new part is the blue word. Okay, the blue word I added there. I add the color blue so that you've seen something really new to you. It's a timer. Every time I mention the timer, I turn it into blue. Okay? So what is the time that you start the timer whenever you send the data? Right? You only have one data to send. So whenever you receive something from an application layer and try to send it out, you start the timer. And when you should restart the timer? You restart the timer means that, okay, timer reach 0, goes off, and then you immediately reset it, let's say 1 millisecond. Reset it to 1 millisecond, and let it count down, and that's what we call reset timer. And the event is timeout. Whenever you timeout, then immediately you send out the retransmission and start another timer again. Okay? So this process will go indefinitely until you receive something good. Until you receive something good, which is an ACK, as your expected sequence number, then you can stop timer. Okay? So this is when you start and stop the timer. Okay? Now, what is something extra in this figure? I just copied it from the textbook. So the textbook makes some adjustment. So let's take a look at what is the adjustment. The adjustment is, if the received ACK, this is ACK, right? You receive something. The ACK is corrupted. Okay? Or not corrupted, but the ACK, the number is wrong. Ooh. What is it? What is it about? It's corrupted. That means that the old case, right? The old discussion that, oh, corrupted, immediately I should respond it. But this, the upgrade is actually doing something lazy. If I see something not okay, corrupted, or of course not okay, and unexpected ACK number, okay, it reduce something, okay, it chooses to do nothing and waits for the timer to go off. Waits for timeout, and as if they reduce the two guys handling into one. Okay, so understand this point? It reduces two handling into one. Okay, of course it will slow down the protocol, right? Whenever you receive an error ACK, of course I want a response, but it said no. Please wait for timeout. Okay. So any other point? The point is what happened. Or what happened? Where can you find this events? Okay, is the time that I don't have anything to send out, still I receive ACK. Okay, where can you find this states? Where? Yeah, give you some time. Where can you find this states? I don't have anything to send out, okay, but I receive ACK. Where? Then you can give me some coordinates, not coordinate, direction, or southeast, southwest, okay? Any idea? Which note? Which note can you find this? We have 4 notes here. Okay? Can you find this in this note? No? Here? No? Here? No response, no. Okay. Here? Also no response. Then which one? Not written there. Okay, I have box. I mean this stage, right? I don't have anything to send. Okay, make it specific. I don't have anything to send. Yes, if I have thing to send, it will be sequence number 0. Okay? If I have thing to send, the next guy send out will be 0. Yet I'm waiting for application layer to give me something. I receive ACK of sequence number 1. Can you find this here? Which node? 1, 2, 3, 4. Okay, 1, 2, 3, 4. Go clockwise. The thing is 1. 1 with 1. Okay, 2 and 2 not 2. Okay, 3, 4. No, then I put it in the final exam. Okay. Okay, so yeah, he got a correct answer. 1. So where? Which edge? I give you labels. Okay. 1, 2, 3. Which edge? 2. Okay. This edge. Okay. This event, I should say. Okay. The event is I'm waiting for something from above, from the application layer. Yet I receive a segment, which is not normal. Okay. Which is abnormal, so I do nothing. And can you find the mirror one? The mirroring one is here. Okay, the mirroring one is here. Okay, so then the entire figure, entire state machine will be describing everything that I write in this timing diagram. Okay, I call it timing diagram. Okay, so the sender side. How about the receiver side? Receiver side is easy. Okay, the receiver side will be the same as the previous version. Okay, you can flip the notes. The last version I call it 2.2. Okay, 2. You don't need to change anything, right? Because the receiver is so passive. Okay, waits for events. The event is where the sequence number is correct or not. Okay, so this is just a illustration of how you can take a look at the state diagram and how this timing diagram reacts to this finite state machine. Okay, the timing diagram goes off with 1, 2, 3. Now consider the fourth message. Okay, with the fourth message, the timing diagram is not finished yet, but in the FSM, we are waiting for a sequence number ACK sequence numbers 1. Okay, and this is the case that this ACK going slow. The ACK going slow. So I will consider there is a timer there, and the timer is reached. Then I will take this edge. So what is this edge? Okay, take a look back here. This edge is timeout edge. Okay, and timeout edge called retransmission, and then I send out the sequence number 1 data. Yet this guy already said that, hey, I will receive a sequence, data sequence 1 already. I'm expecting data sequence number 0. Okay, so as an expected sequence number, yes, I will take this edge to retransmit the ACK. Okay, to retransmit ACK. While I'm waiting for another ACK comes, the old ACK arrives, so I transit. Okay, transit to one state to another, and the story goes on. Okay, so you can take a look by yourself. Okay, it's already not an animation. Okay, just a page by page PDF animation. Any question you want to ask? Any questions? If no questions, then we would migrate to the next part, the sliding window protocol. No questions, huh? Remember, this is the basics of TCP. TCP is really doing something like this. Now we migrate to the next version. Okay? No questions, huh? Good. So what is the next? Next is some motivation first. Okay? So RDT, Reliable Data Transfer 3.0, okay, which is a good protocol. I always love to say that it's a ping pong protocol. Only one ball flying on the table, and that ball won't introduce any out of other packets because we don't have a chance. You don't have a chance. You only have one ball flying. Okay? So we can recover corrupted packet. We can compensate lost packet. We avoid out of order packet. Okay? So it seems to be working. I used to have this entire RDT 3.0 as an assignment. Okay? For how many years? I suspended this assignment for 3 years already. Okay? Because no one, I mean really no one, but only top 10% of the students can tolerate the workload. Okay, the specification of this RDT 3.0 is over 50 pages. 50. Okay, 50 pages. I describe totally 6 threads. Okay, interacting together. Okay, so I need nearly 60 pages of a specification to describe every cases. Okay. And those people, even they choose to have a Java implementation, okay, they find it horrible, so I cut it out, okay. So if you want to do it, I can give you a specification, okay. Yeah, 50 pages, at least 50. I remember last time it's 55, okay. So about performance, I already say that this is a ping pong protocol, only one ball. No matter what is the size of the ball, okay, you cannot grow beyond the underlying media. The media underlying is, let's say, is infinite. You cannot fire a huge packet, go beyond the limit of the infinite. Okay, so let's consider infinite itself. We try to simulate what will happen if I send out this over this infinite cable. Okay, 1 gigabit per second. Okay, and this infinite cable, I just give a random number. Okay, a random number is 15 milliseconds, traveling at light speed from this point to this point, and traveling at light speed going back 15 milliseconds. I just come up with some random numbers. Okay, and what is the equation here? I want to measure the performance, right? So I want to emphasize one thing. How can I utilize this cable? Am I utilize this cable at a right measure? Okay, so the right measure is I keep this cable as busy as possible, right? Flooding packet into it will be nice. Now you already understand that this protocol won't allow you to do this flooding. So what will we have? Let's take a look here. BC time on the center. What is the meaning of BC time? Okay, the time that you use for sending stuff out. Okay, and what is the time here? The time is between two BC time. What is the duration between them? Okay, so with this ratio, we will understand that whenever you try to send one packet out, at least you need to see a long period of time before you can send other things. And this ratio will be the visualization of the cable. Okay? Then I draw it in this way, okay, if you don't understand this, okay? So this is, I need to put down acknowledgement word here, okay? So the thickness will be similar, but the time is negatable. Okay, this acknowledgement seems to be much smaller. And the segment, later on, I will choose this to be a figure for Ethernet. Ethernet is 1,500 bytes. Okay, later on you will see this number. So that's why I choose a 15 millisecond, so that I can easily cancel it out. Okay, now everything is cool. Then this is the time that we want to measure. And this is the only BC time. And I consider the receiving and the sending of this acknowledgement is negatable, so as to simplify our calculations. Now go. So what is the meaning of D trend? The D trend is this period, the BC period. Okay, so the D trend is I didn't put down 15. Okay, sorry, it's 1,000. I put out. Okay, I always think of another example. Okay, I use 8 times 1,000 bytes. Okay, I still fit internet. Okay, so I send out so many bits and over this bandwidth. So what is the meaning of bandwidth? I never say it, right? I never say what is the meaning of bandwidth. Do you know what is the meaning of bandwidth? Huh? Whether 100 megabit per second is better than 1 gigabit per second. Yeah, usually we say, oh, 1 gigabit is better. But we don't know what is the meaning, right? So what is the meaning of bandwidth? Bandwidth means that whenever you try to send a piece of data, you take times in order to push those data onto the medium, right? To understand what I mean, you need some time to push things on the medium, and the medium is a copper wire. Okay, the device, the hardware, together with the copper wire, introduce some delay. Okay, and bandwidth, the meaning of bandwidth is, let's say the bandwidth is 1 gigabit per second. It means that in 1 second, the entire hardware, cable together, all the entire infrastructure with this infinite 1 gigabit per second means in 1 second you can push 1 gigabit onto the network, and it's guaranteed to be delivered. Okay? Guaranteed to be delivered, not including this 15 millisecond transfer time. Okay? Only guarantee that it is pushed down with 1 second with 1 gigabit. Okay? So then what is the meaning of this calculation? This calculation means that I want to push 1,000 bytes onto the network with this cable, with this circuitry, hardware, so on and so forth. And this entire set of equipments take me 1 gigabit per second throughput. So I go for this calculation and know that 8 milliseconds I can finish pushing down 1,000 bytes. Understand this? And this calculation? Okay? So what is next? I understand that this is the time that I spend in this region. Now what is the time that I spend on this region? Oh, very clear. Okay? This region, the figure is drawn badly. Okay, the figure should be move down this guy a little bit. Okay, I draw it bad. Okay, so the calculation should be this round trip. Okay, before I can activate again, so I need a round trip. So 2 times 15 times 10 minus 3 plus the BC period. Okay, I draw it bad. Okay. These two regions together is total time and I need to spend. What's next? Next is the thing here. The thing here is the BC time. after I do this calculation, I know that my utilization is 0.0027. So how many percentage here? Less than 1%. Less than 1%. So what's the meaning? I don't know what is the cable I give to you. No matter I give a satellite or I give you a cheap router, okay? With this protocol, you can only achieve less than 1% of the throughput of the cable. Okay, less than 1%. Sucks, right? You don't love it. And whose fault? Not my fault, okay? It's the protocol's fault. Okay? So, can you improve the performance? How can you improve the performance? Yeah, one way to improve performance is this. You don't care. You don't care about the ACK. Continuously push as much as data on the network as possible. Okay? Wow, this is cool, right? I don't need to wait anymore. So, that means that I want to transform this figure into this, what is the color? Cyan or green or blue, I don't care. Okay, let's say it's green, okay? The green area become as thick as possible. As thick as possible. And I totally ignore the ACK. Then you will have 100% utilization. You have 100% of utilization, but no guarantee in successful packet delivery. Okay? So that means that there's a balance. You want to have a successful delivery, you have to sacrifice the performance. No matter what is the cable I give you. Okay? So one of the conclusion is I will go for a solution, what we call a pipeline solution, means that I send out some data packets batch by batch. Yet I will receive ACK also batch by batch. And try to don't stop and don't wait. Really try, okay? It may not be successful. Okay? I try to push more and more data out on the network, yet at the same time I acknowledge packet received, and if the acknowledgement tell me that in between there is a packet is lost, I need to do retransmission. Okay? So understand this idea, okay? It's very hard to imagine, okay? Think about it as a table tennis game. Okay? You have 1,000 ball playing at the same time. Okay? And eventually you will receive 1,000 acknowledgement coming back. Okay? Yeah, so the figure is very beautiful. Okay? But you will increase the throughput by increasing the time that you utilize the network. Okay? And beyond that, we will mention three big trouble. What is three big trouble? The flow control. What does the meaning of flow control? Can I send at most, let's say, not at most, at least, can I send 1 million packet per transmission? Let's say I have a buffer. Some people crazy open a global array of 1 million bytes, okay, and say that write 1 million byte. Okay, can I push 1 million byte at the same time? Okay, so this is called flow control. Okay, another is acknowledgement handling. If that 1 million byte transform into, let's say, 10,000 ACK, 10,000 ACK, would you like to handle 10,000 ACK? Okay, it's not the case. Okay, we can do some improvement over this. Okay, and how to detect a lost packet. Okay, and how to deal with retransmission. Okay, one more thing, performance. How much can we improve? Okay, if we don't write any code, just by looking at the calculation, we know that this protocol sucks. No matter how many packets I send out, no performance gain. Then we can forget about this. Okay, so then we'll analyze it. So we call it go back end protocol. This is the first version of a sliding window protocol. Okay. There's one thing called sliding window, and the strategy in implementing sliding window is called go back end. Later on, you will see why it's called go back end. Okay. So the go back end is sliding window protocol implementation, and at most sending n packets or n segments. So that's why it's called go back end. That n is here. Okay. And what we call this is called a window width. Okay, the window of width of n packets. Okay, and then one highlight is, okay, I highlight here. The sliding window, okay, we can improve it. Later on, we will have some pros and cons. Okay, let's have a very basic implementation. Okay, the sender side will transmit all not yet acknowledgement segments at one time. Okay, at one time. Let's say you will wait for a timeout. Let's say the timeout is 1 second. After 1 second, I collect all the acknowledgement data. I will transmit it all at once. Okay? So one more upgrade. The upgrade is the sequence number. We cannot only use 0 and 1 anymore. Okay? Because we have more than one packet flying at the same time. Okay? So we have to grow the sequence number beyond 0 and 1. Okay? And this is a very interesting idea here. Okay? The idea is, should we use unsigned in, unsigned long, double? What is data type? Okay, with a specific data type, let's say it's unsigned in. Okay, then what will this unsigned in affect the value of n? This is a very interesting but subtle detail. Okay, in the kernel, we have a beautiful solution to finish this. Okay, I will describe the solution to you. I hope that I can finish it by analyzing the sequence number on the coming Wednesday. Okay. So, do you need a break? Do you need a break? Okay.